Alright, here we go with Chapter 8 homework review. The first part of Chapter 8, we'll have some more on this next week. And this was mostly all about ideal gas laws, different ways to manipulate them and use them to solve various problems in chemistry. So the scores on this homework were actually a bit better. We were averaging about 10 out of 12 on this one, so that's about 1 point higher than what we've been doing. So it seems like this material took pretty well. That said, there's a few things that we had a little bit of trouble with, and I want to go over a few different problem types where we had averages of 50% or less and try to clarify hopefully some of the misconceptions on those. So the first one that we had a bit of trouble with was measuring pressure. I didn't do any example problems of this in class, so it's no surprise that we had a little bit of struggles here. But really it's not that difficult. You just have to be able to visualize what's going on and then know what to do with the numbers once we have that picture in our head. So here we're talking about measuring gas pressure in an open-end manometer. So it's kind of a long wordy sentence that we gave you here, but let's read it. If the barometric pressure was 0.97 atmospheres when the mercury level in an open-end manometer connected to a flask of gas was 124 millimeters higher on the side open to the atmosphere than on the flask side, what was the pressure of the gas in the flask in torr? Whoever wrote this problem should have divided it up into two sentences, but the point is we need to know what to do with all this information. So if we look at the problem, the first thing we're going to look at is what is the type of manometer we're using. So in an open-end manometer, we're measuring our gas pressure relative to atmospheric pressure, and that means we need to know what the atmospheric pressure is. And when we're reading the information in these problems, barometric pressure is atmospheric pressure. Those two things are synonymous. We use barometers to measure atmospheric pressure. We know that from if you're a weather junkie and you follow the local news and they talk about the barometric pressure, that's the pressure of the atmosphere at any given time. And in this case it's 0.97 atmospheres. And then we're told that the mercury level was 124 millimeters higher on the side open to the atmosphere than the flask side. So when we have an open-ended manometer, there's basically three possible situations. So what the device looks like is we have a flask of our gas that we're measuring, and it's going to be exerting a pressure, and then it's going to be connected to this sort of S-shaped tube here. Okay, so this tube has mercury in it, and it's open to the atmosphere. So on the other side you have atmospheric pressure pushing down, and then if the gas pressure is exactly equal to the atmospheric pressure, the two sides of your mercury column are going to be of equal height. So you have this sort of U-shaped mercury column, and there's going to be no difference in height between the two sides. They line up perfectly. Alright, so I'm shading in the mercury. Now we also have the possible situation where if the atmospheric pressure is smaller, so if the gas pressure is higher than the atmospheric pressure, our manometer is going to look like this. So we have our gas pushing up. It's pushing up stronger than our atmosphere is pushing down, and so that means there's going to be an imbalance here. The gas is pushing harder, so it shifts the mercury over like this, and so we have this height imbalance here, where we have this difference in height between the two, delta H, which is the difference in the pressures between the atmosphere and the gas. And then the other situation, if we have if our gas pressure is less than atmospheric pressure, so atmosphere is pushing down harder than our gas is pushing up. So imagine the two things opposing each other, and the one that pushes stronger is going to imbalance the mercury column in that direction. And so this would be a situation where the gas pressure is smaller than atmosphere. Okay, so these are the three possible situations. Again, here you're going to have a delta H. And for all of these, there's a simple relationship between the gas pressure and the atmospheric pressure. So for this situation, gas pressure is higher by delta H, where delta H is in millimeters of mercury, delta H being the height difference. Here we have our gas pressure is the atmospheric pressure minus delta H. Okay, so these are the three possible situations. And in this case we're dealing with this one here, we're told that the mercury column is higher on the atmosphere side. So the pressure of our gas is going to be our atmospheric pressure plus the height difference. And remember that millimeters of mercury and torr are equivalent units. So we're looking for the pressure in torr, but all we need to do is just use millimeters of mercury that we're given for our delta H. However, we do need to convert atmospheric pressure to torr before we can add it to our height difference. So the pressure in the atmosphere is 0.97 atmospheres, and we will convert that to torr first. So we have 737 torr is our atmospheric pressure. And then our height difference is 124, so we convert that straight to torr. It's an equivalent unit, and so we get 861. Alright, so mathematically very simple, but we do need to have this picture in our head to know which of the situations we're dealing with. Okay, so on to the next one. Alright, so in this problem we have a 5.57 times 10 to the minus 3 moles of argon. It occupies a 256 milliliter container at 36 degrees Celsius. What is the pressure in torr? Okay, so here we have number of moles, volume, temperature, and we're just calculating pressure. So we should immediately think about PV equals nRT. We only have one set of conditions here. We're not changing anything in this sample of gas. We don't have initial and final conditions. So for that, we just need to use PV equal nRT and solve for our unknown, which is pressure. So the pressure is going to be nRT over V. But again, we always have to think about units here. So we're looking for pressure in torr, so we might have to do a conversion at the end. Now when we plug the numbers in here, moles we just keep as is, 5.57 times 10 to the minus 3 moles. R is the universal gas constant, which is 0.0821 liter atmospheres per k mole. The temperature has to be in Kelvin, so it's going to be 36 plus 273. So we have 309 Kelvin for our temperature. And then finally our volume needs to be in liters. So we have 256 milliliter container, so that's going to be equal to 0.256 liters. We just divide by 1,000. So when we calculate this out, we get a pressure, but our pressure is going to be in atmospheres because that's the value of the universal gas constant that we use. So we multiply this out. We get 0.552 atmosphere. Alright, and then when we want to do this atmosphere, this pressure in torr, we have 0.552 atmosphere times 760 torr per atmosphere, so we have to keep that conversion factor in mind, it's what we'll use all the time. And so we get 419 torr. Alright, so that's how we do that problem. In this case, there are no changes in conditions, so we don't need to derive a new equation. We just need to use the ideal gas equation and solve for our unknown. Alright, so here now we have another type of gas law problem. In this case we have a balloon, so a closed container of gas, number of moles is constant. We should always think about that right off the bat, especially when we're not adding any gas to this. So we have a balloon filled with helium, has a volume of 1.5 liters at 90.5 kilopascals and 25 degrees Celsius. So kilopascals, kPa, not the most common pressure unit, but it is one of the SI units, or derived from the SI unit. So it still is an important one. And we want to know what will the volume of the balloon at a pressure of 35 kPa if there is no change in temperature. So in this problem, we're given the temperature, 25 Celsius, but then we're told there is no change in temperature. So from that standpoint, we don't really care what temperature is, because what we're doing here is, trying to derive a relationship between the variables that are changing. In this case, we have a volume and a pressure that are going to be changing, but the temperature is not. So this is actually just an example of Boyle's law, the relationship between pressure and volume. Well, we don't even need to remember that or remember the equation for that. We can start with PV equals nRT. And remember, what we do in this case is we move everything that's constant to one side of the equal sign. While pressure and volume are changing, the number of moles is constant. It's a closed balloon. R is a constant. The temperature, as we're told, is constant. There's no change. So that means PV equals nRT, which is just a constant value. And so the equation we derive, which is Boyle's law, but we can get it from the ideal gas law also, is P1V1 equals P2V2. And then we're solving for the volume, the new volume V2. So that's going to be P1 times V1 over P2. Now when we set up the problem like this, we no longer have our universal gas constant to worry about. So for pressure and volume, we can use whatever units we want, provided in this case the two pressures have the same units so that the units cancel out. So we don't need to convert our kilopascals into anything else. Perhaps some of you try to do that. That would be fine if you successfully did it, but if you made a mistake in that step, of course it could mess up your problem. All we really care about are the relative pressures, P1 over P2. So when we put these numbers in, where our P1 is 90.5 kilopascals, our initial volume is 1.5 liters, and then P2, our final pressure, is 35 kPa. So our units for pressure cancel out, and we're going to get an answer in liters for our volume. And we get 3.88. So this, I believe, was a multiple choice question. And a lot of you picked another answer that I'm not quite sure how you got. But anyway, this is the answer we wanted, and it just was a simple application of Boyle's law when we boil it down to that. No pun intended. Boyle's law, we boil it down to that. Sorry. Okay, so on to another one here. This is a similar type of problem, but here we're changing more things. So we have a sample of gas in a piston cylinder apparatus. Remember, a piston cylinder apparatus means a closed container of gas but with an adjustable volume, so the piston can move up and down, and that can influence the volume of the gas sample. So initially it's 654 milliliters, 1.23 atmospheres, 76 Celsius. The volume is increased to 987 milliliters, and the temperature changes to 54. What is the new pressure in atmospheres? Alright, so here, and then this was a numerical question, so we had variable inputs, so the numbers that you saw might have been different than this, but the way you'd solve the problem is exactly the same. So in this case, we start with PV equals nRT again. It's an ideal gas problem. We're changing initial and final conditions, and remember that PV equals nRT tells us everything we'd ever want to know about a sample of gas. And we move everything that's constant over to one side. So in this case, the only thing that's constant is the amount of gas. We're not told anything about how many moles we have, or we're not told that we're adding any more gas. But all three other variables change. So PV over T is equal to N times R, and this is going to be constant. So the number of moles is constant, R is always a constant. So that means the relationship we're using here is P1 V1 over T1 is equal to P2 V2 over T2. So we take our initial and final conditions, set them equal to each other, and then what we're solving for here is the new pressure, which we'll call P2. So P2 is going to be P1 V1 T2 over T1 times V2. Okay? So we have to start putting numbers in. For pressure and volume, the units don't matter as long as the two on the top and bottom are the same. Alright, so our P1 in this problem is 1.23 atmospheres. Our initial volume, V1, is 654. and then our T2, which is what we want in the numerator here. So here we have to convert our temperatures to Kelvin. So this is the one unit you can't mess around with, temperature. Temperature has to be in Kelvin for any ideal gas problem. So that means our T1 is going to be 76 plus 273. $349. And then our T2 is going to be our final temperature of 54 plus 273, which is 327. Okay, so those are the temperature values we want to use. We put T2 in the numerator, which is 327 Kelvin. And then in the denominator we have T1 times V2, so we have 349 Kelvin. And then our V2, we're told, increases to 987 milliliters. Alright, so we check our units, milliliters cancel, Kelvin cancels, the temperature has to be in Kelvin though, it can't be in anything else. And then when we multiply this out, we should get 0.764 atmosphere. Alright, so our pressure decreases a little bit. And it's going to be in atmospheres because that's the unit we put in. Alright, so that's how we do that problem. This is called a combined gas law problem. There is no named law that deals with this situation of changing pressure, volume, and temperature. But we derive the relationship from PV equals nRT, and then we go from there. So the last two I want to go over are gas stoichiometry problems. That's the last three, sorry. Okay, so this first one here was by request, and it was one that we also had trouble with as a whole. So here we have combustion of coal releases sulfur dioxide into the atmosphere. The following process converts this gas into sulfuric acid. So basically we're doing taking sulfur dioxide, it gets oxidized in the atmosphere to make sulfur trioxide, SO3, and then that SO3 reacts with H2O or is hydrolyzed to make H2SO4. Maybe hydrolyzed isn't the right word, but it reacts with water to make H2SO4. So if each ton of coal produces 8 times 10 to the third liters of sulfur dioxide measured at STP, what mass of sulfuric acid can result from combustion of each ton of coal? 1 ton is 1,000 kilograms. I left out part of this problem. Alright, I want to make sure I wasn't missing anything else. I just forgot the last conversion. 1 ton is 1,000 kilograms. This is a multiple choice question. All of the answers are in kilograms, so we're going to look for our answer in that. You guys got about 47% of you got this correct, and then the ones that missed it sort of had a smattering of other answers. There was no other real popular choice. Now there's a lot going on in this question, so it's a stoichiometry problem, it's an ideal gas law problem, and we have to combine the reaction because we're told we're given a starting amount of sulfur dioxide, SO2, but we're looking for an amount of sulfuric acid, H2SO4. So for this we need to combine the two reactions into one to be able to know the relationship between SO2 and H2SO4. So we have 2 SO2, I'll leave out the gas and solid and liquid things, but we have 2 SO2 plus O2 going to 2 SO3s. And then in the second reaction we have SO3 plus H2O going to H2SO4. Now remember, when we combine reactions we want the intermediates to cancel out. So in our first step we're forming 2 SO3s. Our second step we only have 1, so we're going to double this entire second step here. And that's going to give us a modified second step, which is going to be 2 SO3 plus 2 H2O going to 2 H2SO4. Alright, so then we're going to add this first step here to this modified second step to to get our overall reaction, which is 2SO2 plus O2. The SO3s cancel out now, and we have 2 H2Os going to 2 H2SO4. Alright, so this is the process for making acid rain. So this is what we have for our balanced reaction, and this is important because now it shows us that the molar relationship between SO2 and H2SO4 is 1 to 1. We're given the individual steps. We have a coefficient of 2 in front of SO2, but only a coefficient of 1 here, but we need to modify that second step to be able to combine the reactions appropriately. So this is what we get, and now we can go ahead and start with this problem, and we're looking for a mass of sulfuric acid. So the first thing we're going to do is convert our SO2 into moles. So the moles of SO2 are going to be the pressure of SO2 times its volume divided by RT. So this is an ideal gas situation. We have a volume. We need to convert that into number of moles. Now here's where we have to be a little bit aware of something that I haven't really told you in class, so this is my fault. But this term here, STP, and I don't think your book actually covers this, but we will see it in some of the problems, STP. So STP is standard temperature and pressure. And then numerically what that means is 1 atmosphere of pressure and 273 Kelvin or 0 degrees Celsius. Okay, so that's the temperature and pressure we're talking about, 1 atmosphere, 273 Kelvin. So we're going to put those into this equation here. Our pressure is going to be 1 atmosphere with unlimited sig figs, basically. The volume is what we're given in the problem, 8,000 liters. R is still the universal gas constant. And then the temperature is 273 Kelvin. So that means we have, in terms of moles, we have 357 moles of SO2. So that's the first part of the problem. I'm going to add a page here. Okay, so we have our moles of SO2. We found that from PB equals nRT. We have to know STP to get that. And now what we can do is do the stoichiometry to solve what we're looking for. So we're looking for the kilograms of H2SO4. So now it's just going to be a series of steps to convert. So we have 357 moles of SO2. We go to our overall balanced reaction, which is this one here. So in our balanced reaction we have 2 moles of H2SO4 that form for every 2 moles of SO2 that react. So just like any stoichiometry problem, moles is sort of the linchpin unit, the unit that we need to work through to convert one thing into another. So moles cancel out. Now we can use the molar mass of H2SO4 to convert to grams. So the H2SO4 is a molar mass of 98.1. Okay, so we're in grams of H2SO4, but all the answers are in kilograms, so we're going to have to do one more step. 1 kilogram is 1,000 grams. So when we work this out, let's see if we get the right answer. This is the first time I've done this problem, so I hope it's right. We get 35.0 kilograms, which the answers are in scientific notation for some reason, but that's going to be 3.5 times 10 to the first kilograms, which matches answer choice D on the homework. So this is the correct answer here. Alright, so that's how we do that problem. It's a few different things. We had to combine chemical reactions, which is something we haven't done a lot of, although we did see it quite a bit in the last chapter. But once we had the balanced chemical reaction, then it was using ideal gas law to find the number of moles, and then doing stoichiometry that we know and love. Alright, so here we had another gas stoichiometry problem. I think this one was another one that we had a little bit of trouble with and was requested specifically that I go over it. So here we're looking for how many moles of KClO3 at STP will be needed to produce 22.4 liters of O2 gas according to the following equation. So we have two KClO3s decomposing to make KCl and 3 O2s. Alright, so this is another, again, combined ideal gas stoichiometry problem. So we're looking for the moles of KClO3. So if we're making 22.4 liters of O2, we can find the moles of O2 from that. So we're going to use PV equals nRT. Call it N just to keep consistent with the ideal gas nomenclature. So we need the pressure of O2, volume of O2 times over RT. So we're at STP once again, so that means our pressure is going to be 1 atmosphere. Our temperature is 273 Kelvin. So we're not told specifically what those are, but that's what STP means. So we have 1 atmosphere of O2. Our volume is 22.4 liters. And then our R is 0.0821 liter atmospheres per K mole, and then the temperature at STP is 273 Kelvin. Now you'll notice something interesting. When we multiply this across, we get exactly 1 mole of O2. So there is a conversion factor you could use, which is that at STP, for any ideal gas, 1 mole has a volume of 22.4 liters. Now I'm hesitant to introduce this conversion factor because it only applies to STP, and if you don't remember that key point, people are going to start using it willy-nilly, and it doesn't apply at other temperatures and pressures. But we do see that at STP, 1 mole of gas has a volume of 22.4 liters. So that means in this problem we're forming exactly 1 mole of O2. So if we want the moles of KClO3 that form, and I think based on the answers we picked, a lot of you stopped here and picked 1 mole as your answer. But remember, this is the moles of O2 that form. We're looking for the moles of KClO3 that have to react with to form that. So the moles of KClO3, we have 1 mole of O2 as a product, and then from the balanced reaction we need 2 moles of KClO3 for every 3 moles of O2, and that's how we get 0.67 moles of KClO3. Alright, so this is the answer you wanted to pick. A lot of you picked just 1 mole as your answer, and that again was because you used PV equals nRT properly, but then did not do the stoichiometry afterwards to relate that back to moles of KClO3. Alright, and then finally the last one was one of these problems where you had to collect a gas over water, and basically 93% of you had 1 of 2 answers, and 50% of you had it right, the other 43% of you had it wrong, and those of you that missed it, for the most part, you just forgot to do this key step of including the vapor pressure of water in your calculation. So as I said, the answers that you would get with and without this are close. I went over this in class last time, and some of you still forgot that key step, and we'll have to go over it again to make sure we understand that. So we're decomposing hydrogen peroxide, and we're collecting 75.3 milliliters of oxygen at 25 degrees Celsius and 42 torr. What mass of oxygen was collected? So in this problem, we're again looking first for the moles of O2 that we form, which is going to be the pressure of O2 times the volume of O2 over RT. But the key thing here is that the pressure of O2 is not just this 742 torr here. Remember, this is the total pressure. And in all of these problems, the total pressure is equal to the pressure of our gas that we're interested in plus the vapor pressure of water. We're collecting this over water. There's going to be some gas phase water molecules that are contribute to this pressure. And so we're looking for here the pressure of our gas, which is O2. We need to take our total pressure and subtract the pressure of the water vapor, the vapor pressure. So in this case, our total pressure is 742 torr, and then our water vapor pressure, as we're told, is 24 at 25 degrees Celsius. So those of you that missed this, mostly what you did was you put 742 torrs directly into the equation, but we wanted this pressure here. So now we also have to convert this into atmospheres. So we have 718 torr. We convert that to atmospheres. Which is 0.945. So then we'll put that into PV equals nRT. We have 0.945 atmospheres. Our volume is 75.3 milliliters, which is 0.0753 liters. We have to put in liters because we're using the ideal gas constant of 0.0821 liter atmospheres per kmol. And then the temperature is 25 Celsius, which is 298 Kelvin. So the number of moles of O2 that we have we have 0.00291 moles. And then finally we need to find the mass of O2. Just going to move a page in here real quick. Alright, so then finally to find the grams of O2, which is what we're looking for, we have 0.00291 moles of O2, and then the molar mass of O2 is 32 grams per mole. And so we get 0.0930 grams. Alright, and one of the answer choices was just a little bit bigger than this. I think it was 0.096, and that's the answer you would have gotten if you did not subtract out the atmosphere, the vapor pressure of water up here. Okay, so that's one of the key steps, and most of you that missed this problem missed that, and that's sort of how we set these up to make sure that you understand, that key point of this problem, which is that the pressure that you measure is a sum of the gas pressure and the pressure of the water vapor. Alright, that wraps it up for this week. Keep the questions coming if you have any, and I'll do another one of these in 1 week from now.